Okay, off we go. So here's where we were last time. We were talking about this example using change of variables, right? And remember the setup that we went through last time is that while these equations give us these curves, right? Because of the way they're written, because we've got them written as level sets, right? I can actually use these functions that we're looking at level sets of and use those to define my change of variables function, right? So I've got xy and xy squared. Between the two of them, that helped me define this change of variables function. The problem, of course, is that our change of variables function is going the wrong way. It's going sort of to the left instead of to the right. And what we're accustomed to do is pulling back through this function, if you think about it, would have us changing an integral written on D into an integral written on R, and that's not what we want to do. We want to go the other way. Okay, so now in this case, we could actually solve for x and y and make it go the right way. The point to this example is not to get an answer. The point is to show how to actually do the problem without inverting this function. Right? And in general, it might be more complicated, and that might be sort of inaccessible. All right. Okay, so with all of this set up, what I can compute with u and v as functions of x and y, I can directly compute this Jacobian determinant, where u and v are functions of x and y, and I take the partials with respect to x and y, et cetera, et cetera, et cetera. So that is an easy calculation, and we get that answer right there. Okay, again, not what we wanted. If you look at how the algebra is going to play out, I have an xy integral. I'm going to need to write dx dy as a function of du dv. What is it that I'm going to multiply by du dv to get the dx dy that I need to rewrite? I'm going to need partial xy, partial uv. What I have is not that. I have partial uv, partial xy. So again, the function's going the wrong way. I have the wrong Jacobian determinant. And we're just going to cite this result right here. Beautiful fact right there. There it is. These Jacobian determinants, we write them like fractions because they behave like fractions. And here is a second sense. Again, we talked about the details last time. This is the second sense in which we see that they do behave like fractions. Okay, so nothing to it then. The one that I actually want, partial xy, partial uv, is just the reciprocal of the one that I computed directly. And with that plugged in, the algebra goes through pretty nicely, and you see we have ourselves all together with, let's see, let me get rid of my mess. We have ourselves now a new integral, du dv, nice rectangular bounds, gotta love that, and everything's gone through except for one little nasty little detail, and that is, you'll notice here, my integrand is not in terms of u and v. And that is the one kind of algebraic drawback to having your change of variables function go the wrong way, is you are then going to end up with an integrand that you have to convert. So, okay, how am I going to rewrite x to the 7th times y as being some function of u and v? I'm going to show you how to do it in this case. There's going to be a bit of guesswork involved. The nature of those guesses is going to depend on the nature of the algebra. Every example is a little different in that sense. But here's what we need. I need to figure out how to write x to the 7th times y to the 1 as some function of u and v, and reminder, u is xy, and v is xy squared. So now part of the answer is on the screen right now already, but let me sort of talk you through how I got to this equation right here. I have a product of powers of x and y. I need to write that in terms of products of powers of x and y. That's what u and v are. And if you have a product of powers and you want to rewrite it in terms of products of powers, I propose that it would be reasonable to expect that a product of powers of my known product of powers might be able to produce the product of powers that I actually want. So that's why I did what I did here in purple. This purple structure, that I'm guessing that a product of powers of u and v should give me x to the 7, y to the 1. It's because that's kind of the nature of the algebra that I'm looking at. You buy it? Seem reasonable? It's going to be different every time, right? I mean, if these were different kinds of functions, and if these were different kind of functions, you'd have to speculate a different sort of structural relationship between them. Okay, all right. So in this case, we guess like this, and then you multiply it out and solve, and it's a pretty straightforward algebra at this point. And you can persuade yourself that A and B need to be these values, which, if you put in there, tells you that this thing that I'm interested in is that product of powers of u and v. That then goes, as you might expect, oh gosh, let's see here, oh there we go. That is what goes into there. Everybody, yeah.
So is the reason that we do this because that's supposed to be easier to integrate?
Oh no, it's because I have to. I have an integral that I need to integrate with du dv.
Okay.
That means I need this written in terms of u's and v's. Because otherwise I don't know what x is, and I don't know what y is, and I don't know how to integrate x to the, yeah, right, totally. Okay, yeah.
Where did the a plus b and a plus 2b come from?
Oh, that's just multiplying out this, if you just multiply all this out, yeah, it's a little bit of algebra. Yeah. Okay. All right, now you may recall last time we kind of skipped over the justification for the stretching factor formula. I just kind of pulled it out of thin air and said, here it is, and this works. And again, there's enough going on as it is with that discussion. It's a lot of things to keep track of, which direction and stretching factors, and there's a lot. So I like to delay the justification until after we've gotten a couple of wins under our belt, and I feel like we have that now. So now I want to ask the question, where does this stretching factor formula come from? Reminder, the big idea is that I have a little piece of area in the UV plane, which, when it goes through my change of variables function, will turn into a sort of parallelogram-ish piece of area in the xy plane, and the stretching factor needs to be the proportion, the factor that I multiply by the green area to get the blue area. So we want to figure out how to find what that factor is. I'm going to get my foot in the door on that by just directly computing this blue area. And in order to compute that blue area, I'm going to need to know what that vector is and what that vector is. Now, okay, how am I going to understand those vectors? Well, those are output vectors. And remember, output vectors relate to input vectors by way of the derivative matrix. This is a sort of a fundamental fact about what derivative matrices do. They take input changes, they turn them into output changes. So previously, we thought about this edge down here, for example, as being just a width. And its width is du. Right? It represents a little change in the u direction. But now, wanting to think of it as a vector, well, look, it goes in the E1 direction and has magnitude du. So this, as a vector, is E1 du. So what does the derivative matrix do to E1 du? Well, that's what I have over here, you'll notice. That output is just dg, the derivative matrix, applied to E1 du. Okay, is everybody with me so far? Likewise, then, of course, this vector here, dg applied to E2 dv. Okay, next, this area. How am I going to compute this area dA? That's a parallelogram. What's the area of a parallelogram? Parallelogram in R2, in fact. This is the determinant of the matrix that you get, well, absolute value, of course, but the matrix that you get by making the first edge the first column of the matrix, and the second edge the second column of the matrix. Like so. Oh, yeah. Mm-hmm.
Sorry, can you go through the logic of why you're multiplying it by DG again?
That's what a derivative matrix does. A derivative matrix turns an input change into an output change, right? So this, thought of as a vector, right, that represents a sort of a movement from, like if I imagine that I was here and then I moved to here, this vector represents that change, that displacement, right? Input changes multiplied by the derivative matrix to get the resulting output change. Yeah. Is that cool? All right. So we've got a parallelogram area. It's absolute value of a determinant, and now I just need to compute this determinant. A couple of nice things happen looking at this determinant. You will notice that du is a scalar, and scalars will factor right out. Likewise, dv is a scalar. That factors right out. Nothing to it. Linear algebra. Right? Y'all remember all that from linear algebra. Let's see here. Now the big question, what do I do with this matrix? This is a little bit of a subtlety. Clean up here a little bit. I'm going to talk through how to think about this. There are a couple different ways you could think about this, I suppose. I like the following. Let's think about this first column here. What can I say about this first column? This first column, forget everything else. This first column right here, dg times E1. Rule from linear algebra. When you multiply a matrix times a standard basis vector, you get the corresponding column. So that means that this that I have in orange is the first column of dg. Yeah? Now let me say that a little bit differently. The first column of this big yellow matrix that I'm trying to understand is the same as the first column of dg. Let's look at the second column here. This second column, forget everything else, what I haven't read, this second column here, dg times E2, this gives me the second column of dg. So the second column of the yellow matrix I'm trying to understand is the second column of dg. That means this yellow matrix has the same first column as dg. It has the same second column as dg. And as I like to say, if it looks like a duck and quacks like a duck, it is a duck. So this great big matrix is just dg. Everybody happy with that? It's a tricky move, right? It's a little bit of a fast one, a little mathematical fast one there. If you don't like this argument, an easy way around it is you can just write down dg in terms of its elemental partial derivatives. You can literally multiply dg times these standard basis vectors. You can literally compute these columns very directly, and what you will find is, sure enough, this great big thing is dg. Okay, and so, oh yeah. Mm-hmm. Oh, but they do. So well, okay. So I'll say it like this: this column right here, du is a factor in every element in that column, right? And if you're taking a determinant, having a factor in a column, right? That common factor in the column factors out of the determinant. It doesn't have to be in fact, it shouldn't be in every element of the matrix. It's just one column at a time. So determinant's weird, right? That's just how determinant works. Yeah. Everybody good? Yeah.
Do you always use the standard basis vectors? Like, would there ever be a situation where you wouldn't?
Oh, I mean, it depends on the situation, I suppose. I mean, for making the argument that we want to make here, no. We would just, of course, the idea is that I'm taking an integral over on the right-hand side and sort of pulling back to over on the left-hand side. And so I want to look at conveniently shaped pieces of the domain on the left, and then I have to recognize they'll be weird looking after they go through the change of variables function. But never say never. I mean, I could imagine some scenario where, for whatever weird reason, maybe I wouldn't, but it's not going to be our problem. Yeah. Okay, so all together then, look what we've got. We've got this green area, du dv, multiplied by something to produce this light blue area, dA. So in fact, I have the output area as a scalar factor times the input area. There's our stretching factor, exactly what we claimed originally. Is that a... No? Okay, all right, yeah. Okay, cool. Moving along. 3 dimensions. Same thing, pretty much. Let's see here, there we go, yeah. So, pretty much the same thing in 3 dimensions. Hopefully no surprise. Just walking through it. If you have some ugly domain like this monstrosity, and if that is your domain for some integral, and let's take a moment to recognize what a nightmare that would be, right? If I were to slice up this lumpy, weird solid as it is, there'd be a tremendous number of hitting of corners, hitting of edges, side swiping of faces. Oh, this would be a nightmare of inconvenience to do it directly. But if I can view it as being an image, right, then I can play this same pullback game of just kind of plugging in, right? And in particular, whatever it's an image of, in this case, a nice convenient little rectangular box, that will be the domain for my new integral. All I've got to do is plug in. The easy part of the plugging in is x, y, z is g of u, v, w. That's what the change of variables function is. I'm literally just plugging in how this will give me formulas for x, y, and z in terms of u, v, and w. I then just have to worry about pieces of area. Let's see here. Where's the blue? Here it is. These area pieces here are going to relate to the yellow areas. I say areas, volumes. Sorry, volumes. And there's just, again, going to be a stretching factor. And that stretching factor, good news, it's a familiar formula. Same formula, really, depending on how you write it. It's the absolute value of the Jacobian determinant. By the way, you can go through an analogous argument to this. I think it's a healthy exercise. It's just a 3-dimensional version of this. Same basic ideas. And demonstrate that that is your stretching factor. Yes?
So when the textbook talks about like different types of elementary regions, would you say that like G of R is type 4?
I honestly don't keep track of its point of view on that. There are good reasons for what the book does. Those good reasons don't really apply to us. Okay. So the author there is trying to be rigorous, which is appropriate for certain contexts. That book is, the book is just a little bit higher of a cut than this course is, and so we're not going to worry about that kind of thing. Okay. So I think it's reasonable just to say don't worry about it.
Okay.
Yeah. Okay. Good question. Anybody else? Right. Okay. To give you an example of how to do a 3-dimensional change of variables, I am going to start with a theorem that's very handy that I want to have in my pocket before I start the example. That is, if you have a linear transformation, keep in mind every linear transformation can be written as a matrix. Cool fact, the matrix that represents the transformation is the derivative matrix for the transformation also. Kind of weird. Not hard to check. Pretty straightforward, in fact, to check. You can just write down a matrix. Just write down any matrix. Leave it in terms of like A's, B's, and C's and stuff like that. Once you've got your matrix, write down your transformation. Then take the derivative matrix of it. What you'll find is it's the exact same matrix as A. Very direct plug and chug confirmation. I do think it's, again, a healthy exercise Maybe just to make yourself satisfied, maybe do it for 2x2s if you like. Okay. By the way, we've already seen an example of this. I'm going to flip back real quick to, y'all will recall this example and check it out. Here we have a matrix representing a linear transformation, and as promised, the matrix representing the transformation is also the derivative matrix for the transformation. So I don't know if y'all noticed that last time, but there you go. Okay. All right. Let's see. Oh yeah, question. Yeah.
Is there like a quick intuition on why this might be true?
Yeah, no, it's creepy the first time you see it. Yeah, let me tell you what made me happy when I first saw it. I don't know if, aside from working it out for yourself, even if you work it out, it does still seem kind of mysterious. But think about the single variable version of this. A single variable linear transformation. There's no vector here. X is just a scalar. T of x would be some number a times x. And then what's the derivative? Well, dt. Of course, it's just a. Right? So, not that surprising. Right? It's just that, in some sense, the way we think of a linear transformation being represented by a constant, right? In this case, a scalar constant, kind of hides the fact that, don't forget, there's x's in here, right? And so taking the derivative gets rid of those x's, as it were. But if we don't see the x's, it feels wrong. Yeah. Is that satisfying? Yeah. Good. Okay, let's see if I can get okay, here we go. All right. Okay, let's see. Back to, here we were. Okay, so example where I'm going to use this new theorem is going to be I think, very powerful example of using change of variables. Three-dimensional example, we're going to consider a parallelepiped. Oh, whoopsie. Be in highlighter mode. Okay, that's fine. Okay, so this parallelepiped right here. Now let's take a moment to recognize how this, as a domain for an integral, is an absolute nightmare. Absolute nightmare, as follows. There are 8 corners for a parallelepiped, right? Okay, well, those 8 corners, one of them is going to be your first slice. One of them is going to be your last slice. Doesn't really matter which one, depends on which way you're slicing, right? But the point is that's going to leave 6 corners that will be in the middle as you slice. So we should expect to hit 6 corners. We should therefore expect to have 7 separate integrals to deal with this. Right? This is no fun. Here's how it gets even worse. Some of those cross sections are hexagons. So, it's an absolutely unthinkable nightmare to deal with something like this in general. Okay, very, very bad. All right, so here's the way around that we desperately need. The edges that you're given. And keep in mind, if you want to describe a parallelepiped, right, the edges are kind of the easiest way to describe the parallelepiped. Take those edges, make those the columns of a matrix, and let that matrix represent your change of variables function. Now, why would I make a choice like that? What's this arbitrary choice, right? I'm taking these edge vectors, I'm making them columns. Why would I do such a thing? And the reason why is I claim, and I will explain why, but that would make my parallelepiped the image of the unit cube. Now, how does that work? Well, we can just kind of walk through it. Let's think about what the edges of the unit cube are. The edges of the unit cube are E1, E2, and E3. And let's see here. Let's take these one at a time. What happens to E1 when I put it into this cleverly constructed change of variables function? Well, E1 multiplied by this matrix gives me the first column, namely the first edge of the parallelepiped. Right? Likewise, E2 gives me the second column, gives me the second edge of the parallelepiped. This construction, where I've chosen to make these edges my columns, is crafted just so to make the unit cube go in and come out to produce exactly this terrible domain, this parallelepiped over here. Yeah.
How do you know that E1 becomes E1 and E2 becomes B2 and so on?
Yeah, well, so this is another callback to linear algebra. When you multiply a matrix times a standard basis vector, you always get the corresponding column. Does that sound familiar? Yeah. So when you make the corresponding column what you want E1 to go to, then you get your wish. Does that make sense?
Yeah, or more like how do you know the rest of the cube?
Yeah. So there's you can. I hear what you're saying. Yes, there is a linearity of argument that you can make that will work that out, and that's details that I'll be happy to go through with you separately if you'd like. But that's just kind of some. It's just details. But on plausibility argument, I mean, if these edges go to these edges, I mean, it kind of looks like the cube would be going to the parallelepiped. Yeah. And again, linearity takes care of the rest. Okay. All right, so we have an opportunity to use change of variables. Our domain that we're dealing with, our domain is an image of something nicer. I can say the magic word pullback. All right, pull back through that change of variables function to get my new integral. Don't forget to insert your stretching factor. Now, the stretching factor here is just a matter of computing the Jacobian determinant. Conveniently, I already have the derivative matrix. The derivative matrix is the matrix representing the linear transformation. So that's the derivative matrix right there. And you just have to punch up what its what its determinant is, and a little arithmetic. No big deal. Yeah.
So that's because A equals dt.
Yes, that's exactly right.
Okay,
Yep.
So in this case, since you're given like the edges, that's how you can. Do the edges have to directly correspond? Like E3 has to be the same.
Yeah. Well, I mean, technically no, they don't. I mean, if you there's always this. You can do like this, right? You can kind of cycle the edges. That's okay. That's fine. And then if you accidentally do this move, if you accidentally sort of make a right-hand list and make it left-hand, the absolute value will deal with that. So yeah, you can kind of put them in whatever order you want, but yeah.
Oh, because it's always positive.
Because the absolute value makes it always positive. Yeah.
And
That's
you
right.
should. So in this case, since you don't have any variables in your Jacobian, you should just end up with like a number. Like
Yep.
a scalar.
That's literally a number. I just didn't compute it, but I mean, it's whatever the determinant of that matrix is. It's just some number. Yeah. So what that means then is that the stretching factor, being a constant, it's the same stretching everywhere in the new domain. Yeah.
Can you explain why Z translates to like
Yeah.
0?
I was just getting to that.
Okay.
Yeah. No worries. Okay. So yeah, what's the deal with Z? And let me just clean up the mess. Okay, what is the deal with Z? Okay, here it is. What am I going to do with that Z? This Z right here. Well, notice here, Z. That's the third output of this function. Okay, well, that means it's the third element of that X vector. That means it is the third element of that product. And how do you multiply a matrix times a vector UVW? Well, if you want the third element, you're going to take the third row of that matrix and dot it with UVW, and that gives you that right there. So, short version, take this formula, multiply it out. And if you just multiply this out explicitly, right? A is this matrix, U is UVW, X is XYZ, multiply it out, Z will be that. Okay, and so we have a new integral. This is a much easier integral. Notice, again, it's on the unit cube, so constant bounds, nothing to it. No corners, no side swiping of faces, nothing weird like that. Constant times u, v, and w. Very straightforward integral. Way, 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 way better than what we started with. Okay. All right. Oh, yeah, sorry.
On these types of problems, does it matter, like, the order of du, dv, dw? Like,
Not really.
since you're simplifying it enough, it shouldn't matter?
Yeah, I mean, the main reason that we would care about the order of the differentials is if the shape was such that one of the orderings was bad for sort of geometric reasons, then, which is obviously not the case here because it's a box, right?
I'm assuming that's like the design behind this. Is that
I didn't want to deal with, the problem's hard enough as it is, right? Yeah, that's right. So this is a constant. These are basically constants times u, v, w, kind of going on whatever order you like. Yeah, right. Okay. Yes?
So would you ever have a transformation of this, like a parallelogram like this, where the stretching factor would not be a scalar?
Oh, well, definitely, it'll always be a scalar because by definition it's so scalar means that it's not a vector, right? I think perhaps you're wondering might it not being a constant. Yeah, right. No, it will always be a constant because if you have a parallelepiped, the edges are vectors. That they're constant vectors. They don't move around, right? And so, you're always going to have just literal, scalar constants. You got me doing it now. And so, it's always going to be a constant for a parallelepiped. Yeah. Okay, moving along. So, turns out there is another category of functions that make for fantastic change of variables functions. And it is our coordinate system conversion formulas. So recall, you can think of polar coordinates as being a function. R and theta go in, x and y come out. And students like to think of this as a geometry thing in the xy plane, and sure, okay, fine. But I like to think of it as being a function, so that when we get to this point in the course, I can say, this function is a change of variables function, right? Likewise, cylindrical coordinates, change of variable function in 3 dimensions. Spherical coordinates, change of variables function in 3 dimensions. It turns out that these are just fantastic change of variables functions on a pretty regular basis. Probably the most common change of variables functions that I saw in an undergraduate physics major. Did you have a? Oh, okay, yeah. So very, very common. So we're going to be using these as change of variables functions often enough that it's worth not only computing the stretching factors, but remembering those stretching factors. So here we go. You can compute the Jacobian determinant here, and it is just R. And you can compute this Jacobian determinant here, and it is just R. And you can compute this Jacobian determinant here. Oh, I didn't do this quite right. Oh, come on. There we go. This rho squared sine phi, a little bit different from the others. So there you go, and I encourage you to memorize these formulas, these Jacobian determinants for these change of variables functions coming from these alternative coordinate systems have these stretching factors, R and rho squared sine phi. Now I did just sweep a little point under the rug. Notice our stretching factors, of course, need to be the absolute values of those things. So what's the deal with the absolute values? Are we going to have to deal with absolute values for the rest of our lives every time that we want to use one of these? Hopefully not. How do we get rid of absolute values? It's nice to just simply establish when is the thing that we want to take absolute values of always positive. Wouldn't that be nice, right? If we had a guarantee that the thing on the inside here was positive, or at least not negative, then I could throw away the absolute values, never have to worry about it again. It's, big win. So here's what we're going to do. We're just going to make certain conventions. That's an overstatement. We're going to make certain choices. We don't have to. Our desire for convenience, right? Our inner laziness suggests that we choose certain things to be true. Right? And we make these choices so that the absolute values will go away. Now, I think it's pretty clear if you choose R to be positive, then the thing on the inside of the absolute values, being as it is R, will be positive, and then that stretching factor just becomes R. No absolute values necessary. Likewise, here, same situation. Down here, things do get a little bit different. Here we go. Little bit different here. A lot of students mistakenly think, rho is kind of like R, and so if R was the thing that had to be positive before, I guess I'll just require rho to be positive. And look how silly that is. What would happen in this expression inside of the absolute values if you gave me your assurance that rho is positive? Would that affect whether or not this expression is positive or negative? No, not at all. That's not even the issue. Rho is being squared. Rho can be as negative as it wants to be. It doesn't matter. Don't care. Right? What we need to worry about is sine phi. That's the thing that may make this negative. So we're going to choose phi to be between 0 and pi so that sine phi will never be negative. And that's what allows us to get rid of those absolute values. Is everybody with me? Yeah. Okay, so now just I do want to emphasize this remains a choice. You're under no mathematical obligation. Okay, there we go. No mathematical obligation to actually do this. There is no law that says that R has to be positive. If you want to choose a negative R, all right, but now you got to deal with the absolute values, and I don't know why anyone would ever want to do that. That makes sense to everybody? So likewise, it's very hard to imagine the scenario where you'd have any reason to want to choose phi outside of these values. And so, likewise. All right, so let's see an example. Go. So let's let R be this right here, the first quadrant portion of the unit disk. And with that being our domain for an integral, notice that's going to put square roots into our inner bounds, which means we're going to have square roots in our outer integrand, and that makes for an unhappy integral that nobody wants to do. There's trig substitutions, and who wants to do that? Right? Okay. All right. So I'm going to say that this is a bad domain. We don't like this domain. And I'm going to try to argue now that we can view this as being an image. Specifically, we can view this as the image by polar coordinates of this new domain over here. Nice, simple little rectangular box. And so how does that work? I claim that is the case. Let me argue this for you. Let's look at this edge of that box. And let's just think what is this edge doing? Theta, always 0. R goes from 0 to 1. Where are those points in the xy plane? And they're right there. Okay. All right, now let's look at the next edge. That edge right there. Now this edge here has R at 1. R is 1 the whole way along this edge. Theta goes from 0 up to pi over 2. And I think you can persuade yourself. Think about polar coordinates in the xy plane. That makes that edge. Everybody happy? And you kind of keep going around. Let's see here. This edge there. Okay, theta is pi over 2. R goes from 0 to 1. Okay, so that's that right there. And then let's see here. Lastly, this edge, theta is doing whatever, but notice on this last edge, notice r is just uniquely 0, and that means that that whole edge goes to the origin. And so let's say it this way, the perimeter of this, what I claim is the pullback region, goes to the perimeter of this region, and therefore green goes to blue. Everybody buy it? All right, so with that noted, it's just a matter now of kind of doing the pullback as usual. Our integrand, let's see here, our integrand, x squared plus y squared, how do I write that in polar coordinates? It's r squared. One of our convenient existing, sort of standard relationships between rectangular and polar. Flashbacks to chapter 1. How do I deal with the area? Let's see here. Oh, am I out of colors? Oh, I can use orange. Area over here in the xy plane. Oh, I should use blue for that. Area in the xy plane is stretching factor times area in the r theta plane. And don't forget, we've already computed our stretching factor. I don't need to recompute it. It's already computed as r. I can just stick it in there. Everybody good with that? Just plug it in. Don't forget your stretching factor. And now, check it out, we have a totally awesome pullback. My pullback domain is a rectangle, which means I have constant bounds, which means that this is just going to go through really easily. And let me get rid of the mess here at this point. My integrand is r cubed. By the way, please don't forget to absorb your stretching factor as part of your new integrand. It is part of your new integrand, right? Sometimes students kind of forget to actually absorb that in there. So r cubed, easy antiderivative, 1/4 r to the 4th. Plugging in constant bounds, the single variable calculus here works out really easily. And answer, no trig substitutions, no square roots, no weird whatever ugliness. This was going to be just constant bounds, polynomials, life is good. Yes?
Is the bounds for the dr always going to be like 0 to r?
You're talking about the inside bounds here?
Yeah.
It's going to depend on the shape of the domain. In this case, the shape of the domain happened to be a rectangle. The sort of the left edge, if you will, was always r equals 0. That's a peculiarity of the fact that this is a rectangle, and then the right edge is a straight line, r equals 1. Again, kind of a peculiarity.
So then, but that domain comes from the fact that ours.
The what now?
Where does the domain come from?
The domain came from the fact that you may recall I argued that the image of this is this. And so because this goes through our change of variables to produce this, that's what allows me to pull back to that. That's how pullbacks work.
So where did the pi over to?
That's what I needed it to be so that this edge would actually be that edge.
Okay.
Yeah. So there are particulars here, right? You do have to make sure that this is, in fact, exactly something which when you plug into here produces the original domain. Yeah. Right. Well, we're actually going to see another point of view on that in just a few minutes. Actually, momentarily. Okay. So, yeah, moving along. I did my theta slices here. My theta slices look like this. They are, in fact, as you'll note, perpendicular to the theta axis. They're in the pullback r theta world. Right? And here's the thing. Those slices perpendicular to the theta axis like this. Yeah, I can see them right here. They're in the r theta plane, sure, but notice you can also kind of see exactly what they look like in how they show up in the xy plane. Right? So this edge right here, Right, that thing right there, that represents a constant value of theta, and then we look at various values of r as r increases, and so that would be something like that. Each one of these as you go up represents a different constant value of r. Different constant value of theta. Sorry. Right. So here's the wonderful little observation. Sure, I can pull back to my new domain that I got to figure out what it is and worry about. Wait a minute, when is that pullback domain, et cetera, and then I can slice up as usual, or I can take my existing domain and just see what the theta slices look like and just literally do theta slices like this on my existing given domain. It's the exact same process. And likewise for your R slices, if you should ever choose to do them in that order, which I don't think any of you ever will. I never do myself. It's always better to put the theta slices on the outside. So here's that same example. Now I'm going to go through the exact same example, this time from sort of this other point of view. So I've got my pullback domain, and yeah, sure, I can think about all these constant values of theta on the left, or I can instead just kind of think about this process representing constant values of theta as I go through like that. I can think about first and last. Right, so my, let's see here, my first theta slice, you can see in the pullback domain is at theta equals 0. Well, check it out. I can totally see that over here too. That theta slice is where theta is 0. Likewise, my last theta slice, yeah, okay, I could see that literally in the pullback domain as being that's where theta is pi over 2, but I can also totally see that just as well, that this last theta slice is where theta is pi over 2. Just thinking about how polar coordinates look in the xy plane. So I observe you don't even really need to draw the pullback domain. Why bother? Right? It's just a, kind of clunky approach, really. I mean, if I can see everything I need to know from it, from my existing picture, that's the easier way to do it. Right? So altogether, then, here's the what the entire process will look like as I'm proposing. We will talk about theta as going sort of from, let's see here, theta equals 0 up to theta equals pi over 2. There's my theta bounds. Now I will fix a value of theta, some arbitrarily, let's fix theta something like this, and then let's see my first value of r. R is going to start at that point, which is where r is 0. And it's going to end at this point, which is on this curve, which this being the unit disk means r equals 1, and that gives me my inside bound of 1. And notice that the whole process took place on my existing picture, didn't need my pullback at all. Everybody all right? I think this is the way to go. I mean, you can draw the pullback if you want to, but you really don't need to. Okay, so let's see some more examples of this, approaching it in this way. Here we have an integral. There's our domain. Again, you could pull back if you like, but so much easier just to view that I'm going to start at theta equals 0, and then theta is going to range all the way around. And let's see here, I regret my notation. There we go. Okay, so theta starts at 0. Theta then goes all the way around. Now I stop when I'm done tracing out my solid. I stop, therefore, when I get a full turn around. That's where theta has now grown up to 2 pi. And so I end with theta equal to 2 pi. Yeah? And now, okay, let's fix a value of theta, some arbitrary value of theta. Let's see here. Fix a value of theta like that. And now let's think about what r does. R starts at the origin, where r is, of course, 0. And we end at, this point here, and that point is on this curve, which is the unit circle, where, of course, r equals 1. Everybody buy it? Didn't have to draw the pullback. Yeah.
Are there any other applications when like the domain is not like circular? Like
There are a few. Yeah, I'm going to show you a few examples. Yeah, totally. Yes.
It's one because it's the circle.
Because it's the unit circle. So this our domain was the unit disk, and that means that its boundary is the unit circle, and that means that's where r is 1. Yeah. Right. Now back to your question real quick. Yes, circles are a one of the big tip-offs that polar coordinates is going to be very convenient, but they're not the only example. I just wanted to start with some kind of easy, warm-up examples. Okay. Right. Okay. So again, single variable calculus. Finish it up. Y'all can read all that. Let's see here. A couple of tips that I think are very prudent to follow. I advise that you always do your differentials in this order. If you're going to do polar coordinates, just always use this order. It's not that I couldn't conceivably manufacture some example where it would actually be easier to go the other way, but it's pretty unnatural. And I'll say in my undergrad physics major years, I never, not even once, saw an example in the wild where it was better to do it the other way. Never happened, right? And I feel like if I can get through a whole physics major and not encounter that issue, it's not an issue, practically speaking, right? So don't worry about, always choose this order here. Now that said, related to that, when you write down your differentials, students are accustomed to writing down the differentials and then proceeding to think about other things. I think this is a bad idea. I want to strongly encourage you always to write down the stretching factor at the same time. And the reason why is that if you just write down dr d theta, there's a lot of other things to think about. You've got to look at the shape of the domain and think about what your slices look like. And, my ending value of r is on this curve. What's the formula for that curve? And I'm going to have to convert from rectangular coordinates to polar coordinates. And you can get distracted. And after you're done finding your bounds and converting your integrand, it's so easy to just accidentally forget. I've seen it a million times. And it's bad. It's a big deal. If you think about it, the stretching factor is the multivariable calculus idea of change of variables. That stretching factor is the only part of change of variables that isn't just plugging in, right? So it's from a points point of view. Even if we're just thinking about this from strategically on your part. Golly, this is going to be worth it could be worth as much as 4 or 5 points. That one thing, that's just writing down an R, right? Don't leave that on the table. Get that. Get those points, right? In fact, on a question where the solution is to use polar coordinates, if you just write down r dr d theta and turn the page, you probably get 4 or 5 points just for that. Right? So easy money. This is good news, not bad news, right? Always write r dr d theta all at once, all at the same time, and get those points. Okay. And then of course the slicing process as before. You look at various points that are on certain curves and like that. I'm going to end with this example right here. This is actually really quick. If your domain is this shape right here, this annulus, notice that you cannot make any reference to integrals over the solid disks because the integrand is not defined at the origin. And this blue annulus does not include that problem point. There's no issue with the question. But if you make a reference to the solid disk or to this bigger solid disk and then talk about rules of integrals or something like that, you're talking nonsense because there are no integrals on those disks. By far the best way to do this example, you can see how rectangular would be a horrible nightmare of 4 separate regions, that each of which has circle bounds, which are going to involve square roots. Nightmare. But very easy in polar coordinates. Theta goes all the way around, 0 to 2 pi. R goes from, well, let's think about this. It goes from the inner circle that has that equation, which gives you your lower bound where r equals 1, and then it ends at this outer point on this outer circle that has equation r equals 2, which gives you your upper bound. All right, y'all, have a good one. See you later. See you on Wednesday. Let's see, and don't forget to make sure I mark you as present.